engineer from University of Michigan-Dearborn. And he is very well known in his area. He has a number of awards and several papers and grants. And what I think is very exciting is that although I would say, and we'll obviously hear more from him, but he would pass as a software engineering person. And yet he started working in AI, which I think is what's very exciting for this group here, and hear more about this new area of software engineering intelligence. And Marouane has also started along with his colleagues at Dearborn AI Lab. So we'll hear a little bit, understand from that. So we hear what's happening in the neighborhood of AI and maybe single ideas that we could come up with.
Great, thanks Rhoda. Thanks for the invitation. I'd like to share with you some of our recent research on software engineering intelligence, mainly related to some intelligent bots that we built to help programmers, whether automatically documenting their code or fixing quality issues and so on. But before that, I want to take a couple of minutes to share with you some exciting work that we are doing in the center that we established, which is the Dearborn AI Research Center, which is now supported by most of the big national companies. So I'm the founding director of the center, but I'm not alone, of course. I have now 36 faculty from different colleges, College of Business, College of Arts and Science, and College of Education. And the faculty, they come, of course, from broad areas, business analytics, and not mainly just, related to AI and computer science, but brought from all the colleges. And also, we try to establish first with the industry partners different thrusts of the center. So our way to approach the center was to go to companies to understand their needs in the AI and data analytics space. And based on these pain points, we try to jointly define this trust together. So we have mainly focus on smart mobility, human-centered AI, computational intelligence, NLP, recommendation systems, intelligent data analytics, and now we are moving to have clusters of hiring within this area, which is the next step of the center. So we have different trusts, but also have the external advisory board, which is mainly composed by the executives of big companies who are helping us to shape the vision of the center. Again, the way how we are approaching this is not to tell them what they should do, but we try to approach them to understand their pain points. So we found that this are the 5 probably dimensions why industry they would be interested to join an AI center. We found several of them. They're interested to establish collaboration at the small scale level, like some case studies. It could be sometimes even understanding the state of the art without having like any, like deliverables. But also we found a lot of interest in terms of customized tutorials, like customized certificates for them based on their need. This is, one of their pain points as well, because they want to have their employees getting trained on risk advances on AI. And also early access to hiring, also industry benchmarking. I know that here we are organizing a wonderful symposium on AI, and we'll be organizing a one on April 30th and May 1st, which is more probably, let's say, industry focused. We have executives panel, hands-on tutorials, and so on. So we find this is important for industry partners because they want to understand as well what other companies are doing in the space of AI. And of course, we give them access to our weekly reading groups and so on. So this is kind of the summary of what the center is doing and our vision, where we are trying first to try to connect with industry partner. They're working on specific research projects with them and think about sustainability, like we'll be working on master agreement with them, especially from IP perspective, and so on. So I want to encourage you as well, if you want to join our symposium. It will be 2 days symposium, and you can find more information on dair.umdearborn.edu, where we have mainly hands-on tutorials, so it will not be mainly courses on, some of the theory of some of AI algorithm, but will be more hands-on tutorials how this could be used in practice. We have even companies like IBM, they'll be giving tutorial on how to use the IBM Watson Studio, for example, for specific case studies. We'll have eBay presenting some of their recent open source API on behavior analytics of users, and also we have panels of executives, mainly C-level executive VP from eBay, Microsoft, Apple, MasterCard, Ford as well, and having demos and clusters and so on. So I highly encourage you to attend if you are interested, of course. So the current partners of the center are quite diverse. So last term I was working on this, and we established several agreements with them based on Gits and trying to get them involved to champion each thrust of the center based on their needs. So this is just a brief overview. This is kind of what benefits that they could get out of these memberships and so on. And we have now 15 of our advisory board. These are 8 of them, and as you can see, we targeted many of the executives of like CTO of IBM and many others to be part of the center. So also, if you want more details about the symposium, you can find that on the website. But as I said, it's more kind of intersection between what we want to do in academia here and also understanding relevant problems from the industry partners. So that's about the center. Any questions before that? Good. So thanks, Ada, for the introduction. So I mainly work, as Rada said, kind of the intersection of AI and software engineering. So I'm running this great team of very motivated people who are working on different problems that some of them I will be discussing today. So recently we were working on putting the foundation and the community around this software engineering intelligence, where we are trying to bring people together from both the computational intelligence community and the software engineering community to sit together in several workshops and trying to work together on explaining why AI is relevant for software engineering and what could be the targeted problem. And we are writing systematic literature review now with different leaders from both community to put the foundation of this field. So what I'll be sharing with you today are some of the outcomes of this brainstorming that we did around this area, but also some concrete examples that will take me based on the intelligence bots that we want to that we are developing. So in terms of defining software engineering intelligence, we found that one way to define it could be as a way to combine learning, search, clustering, and NLP techniques to find relevant solution in the context with a minimum interaction effort. Because for a long time, especially I'm talking about the software engineering field, whether I talk problems like bugs, localization, or requirements analysis, or program repair. So there were a lot of work where they use it different intelligent methods in isolation. But we found that due to the scalability of software systems and also the very subjective nature of most of the problems in software engineering, you have to combine several of these intelligent methods, and we were looking how you can actually do these combinations that could lead to some acceptable results by the programmers. And we found that some of the interesting, probably specific characteristic of looking to solutions in the software engineering domain is the relevance, not mainly the correctness. And I want to explain that in a little bit more detail. So for programmers in practice, they will not accept in general your solution because it is correct. It should be as well relevant. And relevance means whether to their context, like, for example, you are making recommendation of code changes that are correct, but in files that I'm not owning as programmer. So ownership, for instance, is very important. And we have to analyze what changes programmers are introducing to their file to find that ownership and then sending that ownership that could lead to relevant solution for their context. The same thing, context is very important when you talk about release deadlines. For instance, when managers are working with their development teams, they always put deadlines for them to achieve their code and to release their code. And here the context is as well very important, simply because Some of the solutions that are correct could be requiring a lot of effort to implement now, so they may need to postpone them later. So if you are planning to design a bot to solve the problem, you need to consider the context in a way that your bot could understand that time dimension and that pressure to release the code to make relevant solution. And also, we found that interaction effort, especially in the software development world, is also very important. So if programmers need to interact a lot with your system and giving you feedback, and your system is not able to understand that feedback and behave in a different strategy and different way to actually adjust the solution, you will end up that they will never use it actually in practice. So software engineering offer all this, I mean, a great paradigm for actually trying to think about how we could learn from preferences. So programming is very subjective, design is very subjective in general. So how we can actually learn preferences of program, especially nowadays, I mean, GitHub, provide this tremendous and large set of data that could be used to do all the learning work in order to understand your preference and personalize the recommendation. Finding trade-off is very critical in software engineering in general, because you have to deal with limited resources, deadlines, but at the same time you need to meet some quality standards, you need to manage technical debt. So it's not a simple, looking for a simple solution to solve a problem like generating test cases. It depends on the whole context. And your solution needs to be actually finding trade-off between all these conflicting objectives that could be done through multi-object optimization and any other techniques. And we find that in the software engineering field, for most of the problem, explainability is very important, especially when you deal with programmers in practice. So we have seen a lot of research in software engineering, published papers that promise tools that can fix bugs and improve quality, but when you use them in practice, the programmers need to trust the results, and they will trust your results not because you show them a high confidence level or a specific score. They will trust your results if you explain to them why this is a good solution. If you are saying that this is improved understandability, I need to see the pattern in your solution that actually lead to improving the understandability of your code, of my code, and I can tell you, yes, whenever I want to improve understandability, I would use this kind of pattern of code changes. So explainability is very important when it comes to solving software engineering problem. And also we found relevant problems in software engineering about unifying tasks, like programmers, when they work in practice, they work as kind of in a multitasking way. So they make changes, they test it, they go back to make changes again, but we are still treating in software engineering research and practice problems in isolation. Why? We should try to unify these tasks and look into the dependencies between them. And finally, there is a tremendous need in terms of finding intelligent and designing intelligent bots that could be realistic in their behavior. And again, I want to come back to the definition that focuses on relevance, because even when we try to deploy that with some of our industry partners, the main challenge was that realistic recommendation, that it's beyond finding something correct, as I will show you later. So based on what we have seen, in existing research, a way to define software engineering intelligence is kind of an intersection of a lot of work done in software engineering research about automated documentation of the code and the requirements, search-based optimization, including meta-heuristic search, learning and clustering algorithm, and so many problems in software engineering that include finding bugs, fixing bugs, generating test cases, migration problems, and so on. And we may need to take advantage of the recent advantage of AI, but also we need to look at why several of existing AI techniques and algorithms could not actually solve the problems in software engineering. What is missing, in this algorithm, what challenges exist that prevent actually their application to this problem. As I will show you today, how we combine it with several clustering and multi-objective to solve the problem in an interactive fashion, and we ended up to actually design a new multi-objective algorithm that can feed for specific software engineering problems. So we started to understand what are the specific of this software engineering problem that make application of this technique not really straightforward to address the problem. So to summarize, these are kind of the 5 dimensions to answer why software engineering intelligence. So the first one, in software engineering we have so many problems that deal with prediction. We need to predict bugs. We need to predict efforts for a program. So we focus a lot on prediction in software engineering when we manage actually software development. The second thing, searching in a combinatorial space, because we have, with the current scalability of software system, the number of potential searching could be huge, and it could be, a huge sequence of code changes that need to be checked, and also finding trade-off between conflicting objectives is actually very important. How can I minimize the effort and at the same time maximize the quality? So this is another reason why I need to use this technique, and also learning preferences is the key. If you want to have your research used in practice, especially by programmers, learning these preferences is actually very important, because programmers, they're quite picky when they are, using tools in general, and they can easily, be against your recommendation. So understanding ownership, like using GitHub data to understand what changes were introduced by these programmers, what are their preferences, and trying to personalize your recommendations is very, very important in software engineering problems. So this is kind of the 5 dimensions that we think, like, if you find that there is a need to address any of this kind of problem, you have to use and be within the software engineering intelligence.
Is there any meaning to the size of the...
Yeah, so that's actually connected to our systematic literature review. So actually we come up with these 5 dimensions by analyzing all existing papers that use different techniques related to AI to address software engineering problems, and we found that, for example, this dimension number 5 was actually the main reason why they use AI in software engineering, but we found less probably reasons that we found in papers that talk about scalability, probably because it's evident, or probably because in our research we didn't, probably in the software engineering community, focus on scalability a lot in terms of validating our research work. It could be some of these reasons, but yeah, the size are actually connected to the number of papers that we found in our systematic literature review that we just published in the ACM Computing Survey Journal that explain the different sizes. So for more details, you can find, how the papers actually connect to these 5 dimensions. Any other questions? Cool. So to summarize, so we talked about subjectivity, we talked about conflict objectives, scalability, the need for a diverse set of solutions, especially from software managers' perspective, the need for dealing with interaction effort, and the need for multitasking. So I will not probably cover all this dimension during my talk today, but I try to select some specific problems that cover some of these dimensions. So one of the questions that you may have in your mind, you may say, okay, so I talk about using or adopting or designing this intelligent method for software engineering, but people, they were doing that for almost any engineering domain, right? Electronic engineering or any domain, people, they're using this kind of methods, but what makes software engineering different as well? So if we look to how people, for example, they do optimization and they apply optimization in other engineering fields, what they do most of the time is to kind of build a model that simulates your real engineering material. And then they will apply this intelligent method on that model rather than actually trying to apply the solutions on the real one. So because if you want to calculate your fitness functions or the quality of your solution, you can't actually run it on the real system. You have to run it on in the simulation model. But in software engineering, it's different because your engineering material is the source code, is the model itself. So you can actually apply your solution on the real engineering material. For example, if your solution is the sequence of code changes, you can actually apply it on the system, look at the results, get an accurate estimation of the impact, and then taking a decision whether this is a good or a bad solution. So in terms of accuracy, using AI within software engineering could actually lead to better results comparing to other engineering fields. And thus, we could explain some of the success within the software engineering community around applying this intelligent method. So now I will be a bit more concrete. I will show you how this was actually used in practice, leading to research prototypes that are now deployed in some companies like eBay and others, but also at the same time published in several venues. So I'm talking the first major problem, which is trying to detect and fix code quality issues. So this is actually big, problems that companies were working on that since decades, and there are a lot of challenges to deal with it. Programmers in practice, they're spending over 70% of their time just understanding the code. Because when you join software industry, you will not work on a project or a code that you implemented by yourself. Probably we do that in an academic setting, during courses, but in industry you'll be working on a project that has been there since over 20 years sometimes. So,
is there a breakdown per programming language?
Oh,
I remember as well, it used to be called like it's a write only because nobody could read Perl.
Yes.
Whether there is like a breakdown based on the programming language you use, like how much time you spend.
Yeah, there are some actually studies on this. There are some empirical studies that they were looking to different programming language and how this impact their productivity. This numbers actually come from mainly Java because the study, this number I took it from a paper that do it mainly for Java project. So, and this is a huge waste of time if you can actually improve automatically understandability or even semi-automatic understandability of the code, the ability to fix your code quickly or improve its extendability. That could actually help the company. And also, it's very scalable because, companies like eBay, they have over 10,000 apps. So they can do this work manually. So they need to have an intelligent and automated, or at least some semi-automated support to keep high quality of their code. And this is a huge and challenging problem because it is leading nowadays to even a whole community that we call technical debt community. So the concept of technical debt is very similar to regular debt. In regular debt, for example, if you miss the payment of your credit card, so you will have to pay higher interest later. The same thing happened in the software world. If you have a release deadline and you miss that release deadline in terms of improving the quality of your code or at least keeping the high standards in terms of your quality of the code, you will pay higher interest later, and then your programmer will spend longer time to understand the code and maintain it. Then companies will continue, accumulating this technical debt over time. So what we propose as a solution, it's kind of a solution can help you to move from this side to this side. Of course, which one is easier to work with? Of course, working on a structured stuff is actually easy to do. That's happened in practice. The feeling that you have now, it's the same thing that programmers could have in practice, where this is kind of spaghetti code for them, where it's highly coupled, low cohesion, and they have to spend long time to understand it, to work with it, and even touch it and modify it. So if we can provide solutions and techniques that can help you to restructure your code to make it, very well structured and easy to extend, that could be, saving a lot of time and money for companies and solving and reducing the number of bugs and so on. So there's a whole community around refactoring, where the goal of refactoring is basically trying to restructure a code but keeping the same behavior. So basically you can take, for instance, some large classes in your system and restructuring them to distribute the behavior so it make it easier to modify your code. And this is actually a big problem in industry. So if I take one of our case studies with eBay trying to restructure their architectures and code. So we found when we start our case studies that when you go to ebay.com, whatever keywords you are putting to search for whether products or for anything, it will generate in the back end at least 70 calls to different services and extracting the information from databases and showing you the results of your query. And the 70 calls per one request actually led to 1.2 trillion transactions in the back end of ebay.com per day. And this is actually leading to over $50 million that the company is spending just to actually deal with this huge number of transactions, because when you are calling services and then the company need to pay per transaction, that could be huge, waste for the company. And when we investigated that, we found that the programmers, they were creating a lot of clones, for instance. Instead of fixing the problem, what they do, they just copy-paste the service from one server to the other and creating a call to move it to another service. It works, but this is very costly and it will lead to huge coupling. And what you get at the end is something like this. This is actually the actual calls in the back end of ebay.com during less than a day. And you can see the extremely huge coupling between all the services of their system. So that's what refactoring could do for you. It could reduce the coupling in the architecture of your system, so it could be very beneficial in practice and so on. And this is, a very growing community, and you can see in terms of number of publications, we did another systematic review, and we found that this community is growing, especially recently, because there is a huge interest as well from industry to address these main questions about what to improve in software health, when to improve. It's also a very important question to answer, and we have to do prediction here in order to make this estimation and answer this challenging research questions, and how to improve, which is how you can take code actions semi-automatically to fix that. So there were a lot of techniques proposed in that space. Most of them, they were either manual support, like what you see in general in most of integrated development environment, or fully automated support. I personally was working in this space before, trying to have the dream of fully automatically, repairing quality issues, but at the end, when you try to, use that in practice and get feedback in your empirical study from programmers, you find that it's really hard to fully automate the whole process, because the context is very important. You need to do it based on interaction, and this is the way how we designed our solution, which is different than the current state of the art. So the current tools, the current feedback that we got from practitioners was, this is a very slow process whenever they want to restructure the system. It's boring because programmers, when they join industry, they want to change the world, they want to actually, focus more on functional changes rather than non-functional changes, and it's actually very painful. And even some programmers we have seen based on our survey that they quit some companies because, they found this is really boring to work on either the messy code, or they don't want to spend time working this. So why we try to address this problem using this intelligent methods, because we were looking for a realistic solution. How we can find a trade-off between conflicting software quality metrics. Because if you take coupling and cohesion, they are, conflicting. I need to find a trade-off between them. If I take number of code changes that they have to introduce and the quality of the code, they are conflicting with each other. Although it's very subjective nature, so we need to find a way to show programmers different set of solutions. So we shouldn't show them just one way to redesign their system. So we need to find a way to show them a diverse set of solutions and explaining them the difference between them, because there is no unique design in practice if you want to actually address this problem. Also, we try to make sure that this is language independent, so we created a model that worked for a variety of programming language. We try to address robustness because it's very important to address robustness, especially in the software world where everybody is submitting new commits, new pull requests, so we have to be able to repair your solution based on the change, because it's a very dynamic environment and we use a combination of robust optimization here with multi-objective algorithms. And also we try to make sure that we validate this at the high scale level with several companies. So this was our requirements when we tried to look at this research problem of how we can actually semi-automate refactoring and make it work as well in practice. So we try to address different questions around how we can detect this quality issue in a realistic way, how we can prioritize them, and how we can fix them that can bring different values to programmers in practice, and we use it to validate our work during the empirical studies. If you can fix code faster, if you can reduce the cost of the technical debt, and we can better even manage this technical debt in practice. So this is the first way of how we addressed this problem. So actually we tried to look at this problem from continuous integration perception, and we were, very surprised when we started working on this problem that we didn't find any actually existing solution to actually deal with improving quality in continuous integration environment. Although this is very well expanded, we found, for instance, some bots for reviewing code. We found some bots to generate and find some insights about quality issue, but we didn't find a bot that can actually submit a pull request and fix your code and trying to even explain to you through a chatbot, for instance, but why these changes were introduced and how they could impact the quality of your code and so on. So what we did, we designed a bot that we implemented as a Get app. So you can just subscribe to this Get app, add it to your repository, and then whenever somebody is trying to submitting a pull request or making some comments, so he can activate the bot, and then the bot can do the static and dynamic analysis in order to identify the issues and finding the refactorings, the code changes to fix your issue. Of course, there are a lot of research questions here, like when should the bot actually submit this pull request? This is an important research question because you need to have the bot behaving like a programmer. So in our empirical study, for instance, even before starting with this work, we find that programmers, they feel more comfortable to look at the bot recommendation when they are reviewing other pull requests as well. So probably this could be the right timing to do that. You need to take in consideration the release deadline, the release notes. You need to take into consideration even what programmers are discussing in the wikis, pages, what are the issues that they're discussing now, so you can do the auto-tuning of your bot to fix the issue that they're actually discussing right now in the wikis by the programmers. So there are a lot of personalization to make sure that your bot could behave like a human in order to actually achieve some interesting results and getting them approving your pull requests that are generated. So as I said, we developed this as a Get app, but we give a lot of tuning and personalization of the bot in a way that you can deactivate it, activate it whenever you want based on your needs. You can also customize what quality issue you want the bot focus on them, or you can do that automatically, because at the backend we are using a combination of different learning and clustering algorithms to understand your ownerships of the file, what quality issues you want to target, and also combine this with NLP, as I will show you, to understand what quality issues you are discussing right now using a combination of keywords. So the way how the bot works is we have kind of different quality attributes like readability, flexibility, understandability. So whenever a programmer is trying to submit a pull request, the bot analyzes all these quality attributes. And we were adopting an interactive multi-object optimization algorithm that can actually try to find the trade-off between all these conflicting quality attributes, because as you can see here, so we have all these quality attributes, and every line here represents one possible solution. So the different colors here show different clusters, because the solutions that are in red, for example, they are more or less following the same pattern, so more or less they have the same impact in your code. So probably you can look to only one solution per color to actually understand which solution you may need to adopt. So here is why we combined clustering with multi-objective, because we want to make sure that although we show a diverse number of solutions to the user, we can tell him how different are these solutions, which reduce the time that he can spend on looking at them. And also we can show him the impact of every solution on the different quality attributes. So we are giving some explanation why some of them they are good solutions, why some of them they are bad solutions, and then he can interact, he can accept, reject, modify some of these recommendations through our platform. You can see the code before and after to take a decision whether this is a good or not. So this is kind of actions that the user can interact with the system. So you can see here in a concrete demo how this actually works in practice. So here is how the bot actually was designed and working in practice. So this was applied on JSON, I think. Yeah, it was one of the Google open source projects. So it's a really large scale open source project. So here the programmer is trying to merge a pull request. So this is the pull request that the programmer is trying to merge. So it's touching already to several files, and yeah, that's already, he already modified 10 files. There were 15 comments in this pull request, and then when the programmer is trying to merge it, so the bot will get notified right away, and the bot will go and analyze the files that they were modified by the programmer, looking at all these conflicting quality changes. We have at the back end all the optimization, clustering algorithm, and so on running, and then the bot will submit a new pull request that fixes the one that the programmer actually just tried to merge. So this is the pull request which is generated by the bot. And you can see that the bot modified 12 files, and also you can see all the code changes that were done by the bot, but also we are providing explanations why these recommendations were actually recommended by the bot. So you can see all the files that they were changed. You can see the impact on the quality grade per file, what are the quality attributes that they changed. You can see what code changes were introduced. You can even see the code before and after to actually analyze if this change makes sense or not, and then you can take a decision whether to approve this or not. So you can do it in an interactive way. So in another work, in another paper, we showed how we also consider the interaction with the user as part of our learning data. For example, if you find that the programmer, he always rejects any code changes on a specific file. So what we do, we try to kind of eliminate any recommendations similar to that. So these are the changes that were done by the bot. And as a programmer, you can accept or modify some of them. So the bot behaved like a real, human programmer who can actually interact with the system. So we validated this on several open source and also industry projects, and we really like to see like most of these pull requests of the bot were accepted by open source programmers. So we did actually that in collaboration with some of them, but also with an industry partner. We tried to answer this research question in terms of maybe the acceptability of these bugs and how realistic are the solutions that we are proposing. So it was done on several large projects like Exercis and many other. One of them was the industry projects, and we have several participants who were considered in the evaluation. So we look into the impact on quality, but the most important thing that we try to look at, it's mainly, when this was used in practice, how many of the code changes were accepted, that they found them relevant, and so on. We found that comparing to fully automated tools, we were kind of really outperforming them, and that's one of the main advantages of using the bot. We also find that 9 out of the 11 pull requests that were submitted by the bot during 3 days of work with one industry partner actually were accepted and approved by the programmers, which show that this is actually good work and practice and solve the problem. So another way how we look into this problem is to actually look at introducing some radical changes where people can do this in the cloud, and we run all this optimization and learning algorithm in the cloud. So I can show you a quick live demo of how this actually works in practice. So if you go to refactor.iclab.us, so we have a free academic licenses for this platform, which is based on the work that we did in the past. So here you can see that you can create different categories of tools, because one thing that we found really very interesting, and we just also did another work where we even tried to classify automatically software projects. So how you can create automatically a benchmark that you can use to compare the quality of your projects to other projects. Because for programmers in practice, if you tell them you're improving quality, like understandably by 0.2 or something, that doesn't mean anything for them. How this compare to Google project? How this compare to other projects that they have? So you can even creating different categories of projects and even leveraging several learning techniques for that. How can I cluster different software projects to tell managers or programmers you have to compare this project to other projects, and that's what we did here. So this is a dashboard to show you different, categories of projects that you can compare. For example, between the software projects who are in the science category comparing to the security one, and you can see that the security project has better usability comparing to the scientific project. And by the way, one of our recent NSF project was to actually analyze the quality of research prototypes, many software research prototypes that exist on GitHub, and comparing what scientists publish on GitHub in terms of quality to, for example, industry standards and so on, which is very important, because if we want that our research result to be reproduced, we need to care about the quality of our code, and that's one of the reasons we are making this platform open to be used by scientists, and they can actually analyze the quality of their code, and thus will have to reproduce and even expand their code. So to use our platform, it's pretty straightforward. You just need to specify the Git URL of your project, then put which category you want to compare with, and you add the project. And once this is added, it will be added to this database of other projects. If I take one large open source system, like if I take OpenCSV, in a couple of minutes you can generate a whole report about this open source system. So the total quality index is C, which means it's bad, because we have grades from A to D. And also you can see what is bad in your system, like comparing to the benchmark, like in terms of cohesion, coupling, complexity. So the size of the bar here tell you how bad it is or how good it is. If it is in green, it means it's bad. If it is in red, it means it's bad, and green is good. You can see where these issues are located. You can visualize what part of the architecture has issues, but also you can see what quality issues actually exist comparing to the average of that category. And you can see that this project has probably less effectiveness than the other, and you have the knowledge base here that explains how you calculate effectiveness and understandability, which is based on one of the well-known software quality models. You can even see that at the code level, per file. So you can see, for example, where these issues are located per file, and we built here a model that can actually predict the bugs likelihood from the current quality of the system. So we took a huge data set that we calculate all the anti-patterns, quality metrics, and we try to link that to the appearance of bug. And this is very important for programmers because they will take actions and fix this file. If you tell them, you will see probably a lot of bugs in this file. Like with this file, for instance, we are expecting a large number of bugs to be involved in the near future. And then you get how to fix this. So it depends on your need. Like if you want to focus on, this is based on, again, on clustering and multi-objective optimization, where we can find trade-off between different quality factors. So if you want to focus on extendability, for instance, of your code, you can select this solution, and you can see the different code changes that you have to apply and the impact of the changes. So here you can see all the explanation why this could be a good solution, and even you can see the code before and after to decide if this is a good change or not. And also at the end you can decide to accept or reject this change, and once you click on submit, that will generate a commit to be added into your code base. So this is how actually this work in practice, and this was based, again, as I said, on a combination of using or adapting interactive NHGA2 with clustering and considering the feedback from the user and putting him in the loop during this process. So we have kind of this 4 dimensions where we adapted an NHGA2 algorithm. We rank the solutions by understanding the patterns that exist between good solution and give kind of a favor to those who contain this pattern, so we can rank them based on that. And we do interaction, we pair the solution, we run NHGA2 again. So this is how we did the adaptation. You can find more details in the papers. This is how the different quality measures were calculated, and this is one running example of different solution from this Pareto fund that can find trade-off between the two conflicting objectives of improving the quality and reducing the number of changes to do. And we did also integration with an Eclipse, so you can use it as an Eclipse plugin. So as I said, one of the challenges that we find here, once you start increasing the number of objectives, you will dramatically increase the number of non-dominated solutions, because you have so many objectives. If you start increasing them, so that's when you increase the number of equivalent or non-dominated solutions. So that's why we integrated clustering algorithm here, where the goal was to look at the properties of the solution and trying to actually cluster the Pareto fund, the set of non-dominated solutions, to say how they're different than each other's, then focusing on the one that are really different in your Pareto fund. Then we validated this using different research questions, mainly to focus on the relevance of the solution, and this was done on several open source and industry systems. And this is one qualitative example that we extracted from the results, and you can see that the user can select specific cluster based on his own preference. So if he can see all of this solution, where each of them is a possible sequence of code changes, he can select this cluster. So what happened, the algorithm will start converging to generate more solution in that region of interest from user perspective, And then he selected this cluster, so the algorithm was able to find even more solution in that region of interest. So understanding preferences here is very important. Here was done, again, combination of different intelligent methods for that. The other problem that I will give you an overview very quickly, it's an important one about generating documentation, especially generating pull request description to actually explain the code changes that they were done by the programmer, and generating commit messages. You would be surprised when you see that in practice. I mean, I've seen in one really very big company that almost the number of pull request description was less than 1%. And this was a really big project. So this is a very big pain point actually for industry, because programmers, they don't want or they don't have time to actually document their code, which bring all the challenges why people they spend long time understanding their code and so on. So we developed here a bot to actually leverage combination of NLP and optimization technique to actually generate this commit messages and pull request description. It was a preliminary work since it was the first work in that space. So we are now looking more, to use, we have students work on using neural networks for this combined with deep learning. So we try to leverage what people they did in that space for documentation generation to our problem, but this initial work was basically following this step. So we try to look at what changes the programmer introduced. We try to look at the quality metrics and the code to understand what metrics actually changes. And then we look to the message that was written by the programmer to see if he talked about this quality changes or not in his pull request description or in his commit message. So the first step is to identify if there are missing documentation based on what we have seen in the code. For example, based on metric changes of the code and what has been documented by this programmer. And another work, what we did was even more interesting. We did an empirical study to show that programmers, they were even inconsistent in their documentation of the code. We were showing them that what happened in the code is different what the programmer actually described it. And this inconsistency comes because programmers, they may have used different wording to describe the same thing, because we are lacking probably standards and software engineering when it comes to documentation. So we were able to detect as well this inconsistency. So in this preliminary work, what we did, we tried to leverage the use of open NLP, where we tried to actually go through all the steps to understand what programmers actually documented in their pull request description and what happened into the code. And for that, we tried to actually look to millions of commits, and we extracted the most common keywords that are used by programmers to describe several possible code quality changes. And we found these are the most common keywords that programmers use in practice to actually define specific quality changes in the pull request description. And then we try to kind of use this simplistic way to look at the generation of the pull request, where we try to kind of understand what programmers described it, detecting inconsistency, removing the part of the mission which is inconsistent with the code changes, then adding new descriptions that actually meet what they described. And for that, we use a kind of a template-based, approach or rule-based approach to generate the pull request description. Basically, we try to follow a template that explains what happened, why, when. So these are the questions that we try to answer in our pull request description. So this is one concrete demo of how this actually works in practice. So, yeah, so basically the programmer can accept, reject some of this documentation, so it was done in an interactive way. So basically this is the commit message that was merged by the programmer, and then the bot gets notified to actually check the difference between what was described in the commit message and the actual changes in the code. And then this is the suggested pull request message. So the problem that we are facing now with this preliminary work, that we are generating too much, text and too much, extra information than needed. So we are now leveraging summarization techniques to actually summarize the changes as well to the programmer, which is also an interesting problem. So the programmer can see the code before and after. He can see the documentation generated by the bot, and then he can take a decision whether to accept this or not. So it's an interactive way to generate documentation where we go step by step, showing the changes, why this was generated like that to describe the changes, showing the documented, the non-documented changes. So as a programmer, you can see the why as well, and then you can decide to either accept or not these changes. So also in another work that we did, I'm not covering it here, we worked as well on code reviews issues as well, and we leveraged some of this techniques. So thanks for your attention. So I tried to kind of give you an overview about how this actually was developed, how it works in practice, and if you need more details, I'm happy to share with you different research papers that show more the details of how these techniques actually were adapted. Thank you.
Questions?
Yeah.
Good. So what were the actual synthesis techniques that you used to generate the refactorings?
Yeah, for the refactoring, actually, you mean to generate the code changes?
Yeah, you suggest a change based on a commit. What is the algorithm that actually decides what change to suggest?
Yeah, so actually it was based on some of our previous work where we developed a quality model that described different quality attributes like understandability, effectiveness, and so on. And we validated that quality models based on hundreds of projects to show that it's stable. Mm-hmm. And then what we do, we compare these quality attributes before and after applying the sequence of refactoring. So for instance, we found that understandability was low in this file, and after applying the code changes, the understandability went up. So we can show to the program that if you apply this code change, that will be the impact on the quality metrics.
Searching through the space of all refactorings by taking into account
the quality improvements,
quality
exactly.
Attributes.
Yes.
So it's not, there's a separate phase of suggesting a bunch of possibilities and then about like ranking them according to quality. It's like the search uses the quality attributes.
Yes, because we use the quality attributes as our fitness functions. Okay. So you generate the solution, which is kind of a typical genetic algorithm way to solve the problem. You generate code changes, you look to the impact on the code, and then you compare the before and after, and this will be your fitness function to guide the search toward the relevant refactoring solution. One interesting problem that we are addressing now, we just published a paper on, which is how we can actually extract the impact of the subsequence, because sometimes when you show sometimes 30 code changes to the programmer, they want to know, if I apply this code change together, what would be their impact? Or could you explain to me how this sequence of code changes could be probably decomposed into some subsequence to say that this sequence of refactoring target this issue, this sequence of refactoring target that issue. So we have another work where we try to even look deeper and try to look at the subsequence of the code changes, how they impact the code.
So do you find that the issue is that it's a multi-objective thing? So programmers want to say that this change improves readability, but you're saying it improves like all 10 of these qualities in this.
Exactly, and that's why we use the clustering algorithm as well to actually show you the main different clusters in the non-dominated solution, because we find when we show the whole Pareto front to the programmer, it's too much solution. They want to see 4 probably possible solutions, but not 100.
How much worse is it if you do single objective search?
Actually, we just published the way around that, where we actually transformed multi-objective search to mono-objective search. So what we did, we ran the multi-objective, we do interaction with the user, we know his region of interest already, so we just use mono-objective search to target that region of interest. So basically we translate his preference into weight to the different metrics, because our main problem is actually programmers, they will never tell you this weight to they don't know. I mean, they can tell you this is good or bad, but they will not give you weight to different objectives. So our goal was, through learning from the interaction with the user, we can actually learn this weight and probably just using a mono-objective search at that time. So what we did, multi-objective interaction, then transforming that to a mono-objective search. So we just did that recently.
Interesting. Okay.
Yes?
So in that part where you were auto-generating commit messages, how did you know that a certain change, so to do that you mined GitHub commit messages and then you related them to changes. But what if the commits had multiple changes? So how did you know that which commit changes correspond to what kind of commit message?
Yeah, that's an interesting question, because the challenge that we face sometimes that programmers, when they submit pull requests or commits, they combine in general functional and non-functional changes. Some of the changes are not targeting quality issues, so we have to distinguish between the regular changes that are not refactoring but just regular change, but they may still impact the code, and those who are not probably related to functional changes. So the way how we did it is to actually show to the programmer the potential inconsistency between what he wrote in the commit message and the code changes. So for instance, if you find that we have seen that he talked in his commit message about improving coupling, but when we look at coupling metrics before and after the pull request, we didn't find anything. So we just send a warning to the programmer to tell him, you talked about improved coupling in your commit message, but we didn't find any actual code changes that meet that. So we leverage that as more as a warning system, because of that issue that sometimes you are not quite sure that, okay, we are detecting this quality thing, we want to document it, but the programmer didn't actually mean to do it. That's why we looked at that problem from interactive perspective. But this is, I mean, an interesting research problem, because right now what we are doing is actually using what we are learning from the commit messages to actually guide refactoring suggestion. For example, if you find that he talked about fixing specific security issues, we can look to what he did, but the bot, the refactoring one, could tell him a better recommendation than what he did. So, because understanding refactoring rationale or code change rationale is very, I would say, immature in the software engineering community, and even understanding what do you mean by rationale, it's not, I mean, very well explained in the software engineering community. So we are even running an empirical study to kind of find the taxonomy to explain the rationale of code changes and find the explanation for that. So.
All right. Thank
Great.
you very much.
Thank you. Thank you.